All right, our next lesson is on isomers. I recall that the prefix iso means same. So we'll start off with structural isomers. Structural isomers are compounds with the same molecular formula, but different structures. And there are three types of structural isomers. We have positional isomers, hydrocarbon chain isomers, and functional group isomers. So let's start off with positional isomers. And so as the name implies, positional isomers occur when a functional group appears on a different part of the hydrocarbon chain. So let's take a look at an example of a chemical formula. And I'm going to write it over here just so I have room to do some examples. So consider the compounds C4H8Br2. These are going to be called dibromobutane, but there's a lot of different ways that we can distribute, if you will, the functional group, the bromine group. So let's take a look at our parent chain. So we have 4 carbons. So this is butane. So I'm just going to draw a couple of them, and then I will go through some of the examples. All right, so where on the parent chain can those 2 bromines go? They could go here. And in this case, this would be called 1,1-dibromobutane. All right, so that's 1. Where else could the bromos go? Well, you could have 1 on carbon number 1 and 1 on carbon number 2. What would this be called? This is 1,2-dibromobutane. So you know you have isomers, not if you can draw them differently. I'll show you what I mean in a second, but if they have different names. For example, let's draw our parent chain again. Is this 3,4-dibromobutane? I drew it different than the other 2. This is not 3,4. This is 1,2. We would start numbering from the other direction. So be careful with duplicates. There are many more. What else could we do? We could do 2,2-dibromobutane. We can do 1,3, 1,4, 2,3. So those are all the different ways that we can have dibromobutane. So again, these are positional isomers where the functional group is on a different carbons in the parent chain. All right, so next up we have hydrocarbon chain isomers. This occurs when a parent chain is shortened and the hydrocarbon branches are placed off of it. For example, let's look at all of the different ways we can draw C5H12. When drawing these isomers, start off with the straight chain. And I'm going to leave the H's off right now just for time's sake. What is this called? We have 5-carbon parent chain, all single bonds. This is called pentane. Now with hydrocarbon chain isomers, what we're going to do is we're going to take this off of the end, that last carbon and its 3 hydrogens, and turn that into a methyl group. Well, where can we put that methyl group on the now shortened parent chain? Well, here is our parent chain. So we shortened it from pentane to butane, and where can we put the methyl group? Well, we can put it right here on carbon number 2. What is this called? The 2 is not necessary, so this is just called methyl butane. Why no number needed? Well, if we put the methyl group here on this carbon, that's still on number 2. If we put the methyl group on this carbon here, that's still pentane. So it's got to be, it can only go on carbon number 2. There's only carbon number 2 to put the methyl group on, so no number is needed. So methyl butane. There's one more. Let's shorten the chain further and make it a propane, 3-carbon parent chain. Now this time we have 2 methyl groups, so where must the methyl groups go in order to have propane? Well, there's only one option here. We can't put it on the end carbons. That's going to extend the chain. And to keep propane, we need to put the methyl groups on carbon number 2, both of them. So what is this called? The book calls it 2,2-dimethylpropane. But again, we don't have an option here. The methyl groups can only go on carbon number 2. So dimethylpropane is sufficient. Lastly, we have functional group isomers. This occurs when the hydrocarbon contains a different functional group. So let's take a look at these examples. Let's say we have C3H6O. How can we draw that? Well, here's one way. Make sure you count for all of your atoms. So we have 3 carbons, 1, 2, 3, 4, 5, 6 hydrogens, 1 oxygen. What is this called? That is called, well, what is that? Is that an alcohol, ketone, aldehyde, carboxylic acid, ester? What is that? That's an aldehyde. And so this is called propanol. Here's another one. 1, 2, 3, 4, 5, 6, C3H6O. This time we have a different functional group. This is not an aldehyde. This is a ketone. This is propanone. There's another example in your book, shows the same exact thing here, this time with a longer parent chain, page 1035, 1035. C4H8O, we can draw different ways. And again, there's many more examples of functional group isomers. This just happens to be one. So same chemical formula, different functional groups. Next up, we have the stereoisomers. For stereoisomers, the order in which the atoms are joined is the same, but the molecules have different spatial arrangements. One type are known as the geometric isomers. The geometric isomers consist of the cis-trans compounds. We'll also look later at the EZ compounds as well, but we'll keep it simple for this test. Cis-trans compounds. Alkenes, because the double bond does not allow for rotation, enables it to form these cis-trans compounds. Let me show you what I mean by cis and trans. So let's look at this example again. I'll write the formula over here so we have room to draw these. C2H2Cl2. So with the cis-trans compound, starts with drawing the carbons that are double bonded to each other. So I'm going to show you 2 different ways that we can draw C2H2Cl2. And so we have each carbon, because it is double bonded to the other, has a trigonal planar geometry. And so let's show that. And so one of them looks like this, where the 2 larger atoms, not the hydrogens, are kind of on the same side of the double bond as each other. And when this is the case, we call this a cis compound. So this is cis, and then what is the name? We have 2 chlorines, so this is dichloro. Where are they? The 2 chlorines have to be across the double bond. They can't be on the same carbon, otherwise we don't have a cis-trans isomer. So this is 1,2 dichloroethene. Cis 1,2 dichloroethene. Well, what's the other way we can draw this? We can draw it this way. And again, it's not about drawing, it's actually about these molecules having this arrangement of atoms. And so this time the chlorines are kind of opposite of each other. And so they're pointing in opposite directions. Like in the previous example, the 2 chlorines are kind of pointing in the same direction. And so this one is trans 1,2 dichloroethene. So that's one example. Let me show you another example of cis-trans isomers where it's not so much a larger atom, but we're looking at groups of atoms. So that example is 2-pentene. Now, if we draw it straight, don't draw it straight right now, but I just want to show you. Whoops. 2-pentene. It looks like that. Now, we don't know if this is cis or trans because we didn't draw it the right way. So always draw the carbons that are double bonded to each other first and show their trigonal planar geometry. So let's go ahead and do that. All right, so that's carbon number 2 right here on the left. So we need another carbon. So I'm going to put carbon number 1 here. So that's 1, 2, 3, and I'm going to put my 4th and 5th carbons there. These are hydrogens, just for emphasis, I'm going to put those there. And so, which is this, cis or trans? So this time we're looking at not larger atoms, but groups of atoms. We have hydrogens versus CH3 and the C2H5 group. And so they are pointing in the same direction, if you will. This is cis 2-pentene. What does trans 2-pentene look like? So again, let's start off with this. Double bonds. And I'm going to draw, again, carbon number 1 down here. And this time carbons 4 and 5 here. So this time our CH3 and C2H5 group are pointing in opposite directions. If this is the case, this is a trans isomer. Trans 2-pentene is how we would name that. Another example of cis-trans isomers, and it's not really cis-trans actually, but it's geometric isomers, involves cycloalkanes like cyclopropane, cyclobutane, cyclopentane. Much like with the alkenes, if you have a ring structure, there's no rotation around the bonds, and so all the atoms are locked in place. That's the key here. Single bonds allow for rotation, and so the atoms aren't really locked in place. But with double bonds and rings, the atoms are locked in place. And so there's no rotation, and because of that, this lends to itself to geometric isomers. So take a look on page 1036. We have a couple examples of geometric isomers of cycloalkanes. So starting in the margin, figure 28.1, we have dichlorocyclopropane. And so notice in the first one, the two chlorines are pointing up in the same direction. And then in the second one just below, one chlorine's pointing up and one is pointing down. They're pointing in opposite directions. So the top one would be your cis isomer and the bottom one would be trans. In figure 28.2, at the top of the page there, we have 1-chloro-3-methylcyclopentane. And we have a cis and trans isomer. So this time we're looking at the chlorine and the methyl group and where they are relative to one another. So in letter A, they're both pointing kind of up, if you will. I know the one looks like it's kind of pointing to the side, but they're both pointing up-ish. And then in letter B, the chlorine's pointing up and the methyl's pointing down. And so because of that, that will be our trans isomer. So those are cis and trans isomers. Now, how would you draw that? It's kind of hard to draw the ring structures. It's best if we show kind of three-dimensionally, where we have ball and stick models there in the book. And so sometimes it's a little difficult to draw those 2D. Next up for the stereoisomers, a different type are known as optical isomers. With optical isomerism, it occurs when one carbon atom is single bonded to 4 different atoms or 4 different groups of atoms. This carbon that is single bonded to 4 different atoms or groups of atoms is said to be a chiral atom or a chiral carbon. The 2 forms of the molecule are referred to as enantiomers. Enantiomers are non-superimposable mirror images of one another. So go ahead and take a look on page 1037, and we have mirror image of those 2 molecules. Another example of non-superimposable mirror images would be your hands. So we're talking about handedness. Here's another enantiomer refers to handedness. So if you hold your hands facing each other, they are mirror images of one another. If you try to stack one hand on top of the other, not all of your fingers are going to line up. Maybe we can get some of them to line up, but not all of them are going to line up. So that's what enantiomers are, non-superimposable mirror images. So an example is 2-butanol. And with these type of isomer, I'm going to want you to draw them three-dimensionally. So here's how it works. Let me actually just show you what I do here. It's kind of hard to explain without showing you visuals. I'm going to show two bonds in the same plane because we have a geometric arrangement around our chiral carbon. And so the bonds that are in the same plane are shown with just regular lines. And I'm going to write this as, I don't know, I'll just write it here, C2H5. So technically it's, I don't know if that's the best way to show it, but that's how I'm going to show it here. We could write H5C2. I don't know if that's any better. And then what's most important is I want to show the bonds that are not in the same plane. So we have another carbon. So remember, there's 4 carbons. So 2 here, another one here, and then one more. That's, I'm going to represent with a wedge. So that's pointing back into the plane. And again, this is kind of hard to see. Take a look at the book. Maybe if you look in the bottom of page 1037, all the way left, letter A, that green is pointing back into the plane of the page. The whites and pink are in the same plane of the page. And then you have the red that's sticking out. And to show the atom or group of atoms that's sticking out, we're going to use a wedge, a solid wedge. And for this one, I'm going to put the hydroxyl group there. So let's say we have a mirror here. We want to draw the mirror image of this. And so we have our hydroxyl group here. We have our carbon dashed wedge going into the plane of the page. Hydrogen here. Whoops. Let's scooch that over a little bit. And we have our C2H5 group there. So these are mirror images of one another. If we try to stack them on top of each other, they're not going to be able to be superimposed, but they are mirror images. They have atoms are arranged in the same way in terms of what atoms are bonded to what, but they are just mirror images of one another. So what's the difference between these two isomers? They look very similar. So first of all, we'll get to that in a second. If a compound that contains a chiral carbon is made in the laboratory, then the products will consist of both enantiomers. There's no way to just make one isomer or the other in the laboratory. You will end up with a 50-50 mixture of both enantiomers. This is known as a racemic. That's how you pronounce that word, racemic mixture. However, if a compound that contains a chiral carbon is made in nature by some organism where enzymes are utilized, then the products will consist of only one of the isomers. The two forms of the isomer are known as L or D, or L and D isomers. And that substance will be what we call optically active. Optical activity refers to the phenomenon in which enantiomers rotate plane polarized light. So light consists of waves. If you pass the light through a polarizer, you have only one type of wave that's going through, and then that light will be rotated one direction or the other by that particular isomer. If you pass light through that substance, light will rotate. And so what direction the light rotates depends on the particular isomer. So let's take a look at that. Finish it off. It says L-isomers. L stands for laboratory. Rotate plane polarized light counterclockwise, or left, I guess, if you will. I'm pronouncing those words. So L stands for levorotary, or left, and D stands for dextrorotary, or right, or clockwise. So again, just know that one enantiomer, one isomer, will rotate plane polarized light one direction, and the other isomer will rotate plane polarized light a different direction. That is literally the only difference between those substances. Everything else is exactly the same. All right, that concludes this lesson. Actually concludes this part of this unit. All right, thanks for watching.